Okay, so I know many of you are familiar with GeoDa, and maybe you're not familiar with this GeoDa because this is the one that is the latest version, and I hope you can see this. But one thing that has changed in the very latest version of GeoDa is that some sample data sets are included as you open the program, and they're listed. Several of these we will use in this class. So the homicides by counties, Baltimore house prices. Here's the classic Columbus crime data, some Nepal data that a lot of people use for their projects, data for New York City on social services, and so on. So all of these are available if you don't have any data, if you just want to go ahead and start playing with things. And then this just reflects what I have just been doing. These are the most recent data sets that I used to play around with. So just to set the stage so everybody, give me a show of hands again. Who has used GeoDa before? So there's still a few people who have not. So let me just very quickly give you an overview of the functionality. So the functionality is embedded in this toolbar, but also in the menu on top. It's completely equivalent. And let's just start with putting a data set. This happens to be the same data set as I already have in here, but this is a data set that's available on the Canvas site. So you take a shapefile or any geographic file. GeoDa can read more than just shapefiles. It can read map objects, GeoJSON files. It can connect to databases like PostGIS databases and so on. But you take this file name and you plop it in here, and it opens up the map. So the limitation of GeoDa at this point is that it refers to a single geography. So in this case, this is the geography of the continental US counties. And, but it's important to keep in mind that that's a single geography, but it can be represented in multiple ways. For example, as we'll see later, we can represent the counties by a central point or a centroid. And so these points are points. You may think, well, that's a different geography. Well, it is and it isn't. It's a different representation of the same geography. So they're the same counties, but rather than being represented by the actual outlines of the county boundaries, they're represented by points. And then you can get even more abstract and take these central points and construct a tessellation around them. A tessellation is a regular geometry, for example, Thiessen polygons, which is, if you wish, an abstraction of the actual geometry of the actual county boundaries. So then, rather than representing the counties by their actual boundaries or by the central points, we can represent them by these polygons. Again, is the same geography, but a different representation. What you cannot do in GeoDa right now is combine counties with states, for example, or combine point data with aggregate data. So you would have, you know, locations of farms, and you would have the county that they're in. You cannot do that right now in GeoDa. That's a limitation. But in the same geography, we're in good shape. So you see that once you load a data set, the toolbar becomes active and all the icons get their little colors. And let me just go through this real quickly so you get a general idea of the functionality. The exploratory functionality we won't really deal with in this class. That's what I cover in the fall, or a lot of what I cover in the fall. But so here, this is the first icon deals with opening and closing files. That's just basically how you read data. And let me just get rid of this map and open it again so you see the full range of functionality. So we can pull in files of any number of formats. Um, GeoDa uses the Geos and GDAL libraries, so it can read whatever those libraries can read, which is a wide range of geographical formats. You can connect to databases like a PostGIS database or even an Oracle database. You can connect to web, a GeoJSON URL, or the older Web Feature Service URL, so you pull the map straight into GeoDa. And you can also have a direct connection. If you have an account on Carto, you can get your Carto data into GeoDa. Carto is a web-based mapping and database and analytical service. You can get a free account up to a certain size of data. If you need more, then you pay a subscription, like, you know, Dropbox or any other of these things. So we have a direct connection to Carto. It's very easy to pull your data in. So then once the data are in, as let me go back to the example I just started with, you pull them in and you get the map. The first three icons deal with the management of the data. So you saw me delete the data set. Then if you make changes to the data table, you can save the changes. The next icon is a table icon. If you pull it up, you see the actual contents of the data as just a spreadsheet-like thing. If you right-click on the table menu, you have a number of different options. You can, some of the more useful ones is you can merge data tables. It used to be that GeoDa insisted on a strict one-to-one match of the keys. This is now more general, so you can bring in tables that have more observations than GeoDa does. It only picks the ones that actually match, so it's a little more robust in that respect. And then you can create selections by queries. That's a little awkward compared to some of the functionality in regular databases, but it works. You can also do selections graphically by selecting with a pointer or a selection box. You can create new variables, and you can rename the variables. Just as a practical note, an extremely useful feature is editing the variable properties. Many of you will be combining data sets from, say, census sources with a layer, a shapefile that you got from somewhere else. And what you will find out, it has very often the identifier, the ID variable, is not a number, but is a string. It's a character string. Even though it looks like a number, for example, in the US, the FIPS code, the federal identifiers for counties, they're 5-digit numbers, but many, many data sets provide these as actual characters. So you have 54052, but it's actually in quotes, so it's actually a string. So you cannot treat this as a numeric variable. This is a pain in practical work, you know, and I got so sick and tired of having to do this outside that we brought it in GeoDa. So in GeoDa, you can actually edit the properties of any variable. Just to show you, you see the variable, it's real is real, like polyID is integer. Say FIPS is a string. So FIPS in there is actually a string. If you click on this and right-click, then you see you can change this to an integer. And I didn't show you, but so now FIPS, you see here how the state FIPS and the county FIPS are left aligned, which means that they're actual characters or strings. And you see that the FIPS code is now right aligned, so now it's an integer. And so these are some of the things that the table functionality has. The most useful ones for me are this one, merging data sets, and then saving subsets of a data set. So you can create a subset either as a result of a query or, you know, interactively. and then save selected as, and then you have a subset of the data as a separate data set. And of course, under the hood, GeoDa is a geographic file converter, because you can load in one file and then save as under any of the formats that it supports. So this is handy, for example, if you pull data sets from GeoJSON URLs and want to save them as a shapefile for further manipulation. It is very easy to do in here. So that's the table. Then we get into the real stuff. The W we'll deal with today. That's the weights manager. I'll return to that in a few minutes. This is the mapping functionality. And GeoDa has a range of basic choropleth mapping functions. Most of these are what we call statistical maps, in that they basically give you a visual graphical representation of a statistical distribution, or the summary of a statistical distribution. For example, quantile maps give you the data categorized by quantile. They all the ones in the same quantile get the same color. Special to GeoDa, which you don't have in many other things, is functionality to deal with proportions or rates. Proportions or rates are characterized by something called variance instability, which means that their precision is very uneven. The precision depends on the base. So if you have counties with a lot of people and there's a rate computed for that, that's precise. If you only have 200 people and you have a rate computed for that, it will have a high standard error. And there are a number of techniques out there to correct for that and have a representation of the data that prevents spurious outliers from being identified, for example. So that's all in GeoDa as well. I won't dwell on this. This is a specialized map, is a cartogram, map animation. We have functionality to edit the classifications for your map. This is all more specialized. Then we have standard exploratory data analysis, histogram, box plot, scatter plot matrix, bubble chart, 3D scatter plot, which is really great to look at, but not that great to analyze. Parallel coordinate plots, which are a very powerful way to deal with higher dimensional data. They're basically represented in 2D. If you're not familiar with that, you can think of a multidimensional data set, the observations as points in a multidimensional space. For example, in 3D, they're points in a cube. Well, in a parallel coordinate plot, points become lines, and the dimensions become parallel lines in the graph, and each observation is a line that connects the values on each of the axes. So you can easily add more axes. I mean, if you work with cubes, fourth dimensional space is a little hard to imagine, but you can add multiple dimensions to the parallel coordinate plots, and so you can visualize clusters and outliers in higher dimensions in multivariate space. Then we move to the conditional plots, which are also known as trellis plots. If you're familiar with visualization techniques, these are plots where you condition on two variables. For example, if you want to look at, say, lung cancer mortality, and you condition by income and by education, then you get, say, 9 micromaps of lung cancer mortality for different income groups and different degrees of education. So you can see, for example, whether there's interaction effects between lung cancer mortality and these conditioning variables. It's a very powerful thing, again, to reduce dimensionality and get insight in multivariate relationships. Then we move into the spatial arena. This is global spatial autocorrelation and the Moran scatter plot. This is this is non-parametric spatial autocorrelation. Basically, the Moran scatter plot, as we saw last week, and as we'll see again later, requires a spatial weights matrix to quantify spatial autocorrelation. The non-parametric methods use distance. They use pairwise distance and basically order the covariances as the distance increases. So as the distance increases, the covariance goes down, and you can see, for example, where is the range that the covariance or the correlation becomes 0. That's the range of correlation. So that's in this particular graph. And then these are the various measures of local spatial autocorrelation. There's a few new ones, local Geary and multivariate local Geary, which should be in the next release. This is a host of functionality to deal with data in space and time. So you can create what we call grouped variables that keep track of the timestamp of a variable. So you can do animations and move through multiple graphs and maps and do comparative statics. So you can flip through a graph at different points in time, or you can put them next to each other for different points in time. And related to this is something useful for, at least at a fairly intuitive level, treatment effect analysis. We call it averages chart, and an averages chart starts with a very simple comparison of the means of a variable between a control group and a treatment group. And then you can add a time before and after with control, without control, and you can basically do difference in difference tests, which you may be familiar with from econometrics. And then the last part is the regression part, which is what we'll be covering later in this course. So that's kind of an overview of the GeoDa functionality. What we'll focus on today is the weights functionality. And as I mentioned earlier, that is managed through this W here, the weights manager. And since I gather most of you are not from Chicago, you didn't get the irony of having this W symbol in the fall right at the right time. You know, couldn't have timed it any better. So anyway, this weights manager is now the central part where we do creation, loading, looking at the properties. In earlier versions of GeoDa, these were separate icons. Now it's all pulled together. So let's just start with create. And this is the main dialogue. The first thing I want to emphasize is that any weights file that you create has to have an ID variable, a key, that matches the data set. In most situations in practice, you don't really have to worry about it, but especially if you combine data from different sources, you have to be very careful that what you think is a given observation is actually the same observation in the weights file. And in order to ensure that that's the case, we take a variable, a key in a database sense that is common between the data and the weights, right? So you have to specify that has to be a unique variable for each observation. Typically, you have this in your data set already. And for example, in this data set, we have the FIPS number, which is the FIPS code turned into an integer. But if you don't, then you create it. So if you don't have such an ID variable, then you add it with this button, add ID variable, which would then ensure that after that, there is always a one-to-one match between an observation in the data table, so to speak, and the same observation in the weights file. Why is that important? Because the formats that we use, like a DBase format, they don't guarantee that the order is stable. So just because you see it in a given order on the screen doesn't mean that it's necessarily in that order in the database. And to avoid situation where you end up connecting a neighbor structure to the wrong observation, we have this key variable that ensures that there's a one-to-one correspondence at all times. So if we specify this variable, let's say FIPS number here, then you see all the options become active. And let's say we pick rook contiguity, which we now know what that means. It means common edges. Then you see this option that pops up, precision threshold. This again is something that may bite you in practice. Not all spatial data sets have the same care and precision. In other words, when you think that two polygons or two areas touch each other because you see it on the map, on the screen in front of you, that is not necessarily the case. That is only the case if you have been careful in the GIS part and you have a clean, quote-unquote, GIS. That's actually a technical term, cleaning your topology, making sure that, you know, common boundaries are actually the same numbers, the same coordinates, and not, you know, a little bit off. So in practice, that often is not the case, and then we used to get people emailing us and saying, hey, you know, GeoDa is wrong. You know, county A is definitely touching county B. I can see it on my map, but in the weights file it says they're not, right? And that is because the precision of the underlying digital file where the boundaries are recorded is not clean. In other words, there are teeny little gaps between these boundaries, and so an exact touching criterion won't pick it up. So we allow for a little fuzziness, so a little bit of a buffer, if you wish, around the boundaries to pick up neighbors in that way. Most of the time you won't need this, especially if you're created your own data, but if you get, you know, shape files from who knows where, they're not always in the best condition, and this actually, this is the case. You need this precision threshold for the New York City sample data set. We may have fixed it, but initially, you know, if you created a weights file for that data set, it would say, I can't do this, because the boundaries are actually not touching exactly, you know. So we just say create, then it asks us to make a file name, and one of the problems, and we're trying to do something about that as you'll see in a little bit, one of the problems with weights files is that there are no metadata. So unless you're creative in the file naming convention, there's no way to remember that this actually is a Rook-based contiguity file. You know, there's no record of that. Now, if you create them in GeoDa, and if you save what we call a project file, then it will remember this. Then it will know this. It'll have a record of it. But if you just do it as such, then you have to be very creative. And I, long ago, gave myself the discipline of always adding an R or a Q or a D or a K to the file name so I could roughly remember what they were. So if we do save, then, you know, this is done, okay? And I think to date, this is still the fastest way to create a weights matrix. Try doing this in some other not-to-be-mentioned software, and you will sit there for a while. These are 3,085 counties. So it's instantaneous. It's been like that for years. Now, if we want to do queen contiguity, same thing. You know, we set the file name. That's the slowest part. And then we create it. Yeah, I'm going to replace it. So now you see in the weights manager, there are two files included. And both of these have, in the little box at the bottom, some properties. For example, it knows that it's a queen weights file. It knows that it's symmetric initially. This is important later on when we will deal with some of the estimation methods. It tells you the name of the file, obviously. Importantly, it gives you the name of the ID variable. So all that information is known now, but let me show you something. So let me take the Rook file, and you see we have all the information. It knows that it's a Rook. All that stuff is there. I'm going to remove it, and now I'm going to load it. So I'm going through my list of files, and here's the Rook file that I just created, and I open it. I want to see what happens. Type, no idea, right? Symmetry, I don't know. The only thing it does know is the ID variable, because that is kept in the header file of the weights file that is created. But everything else is gone. Yeah?
Does it create these weights based on the map or based on the underlying data?
Based on the underlying boundary file.
The boundary. So it doesn't matter if I have counties or states. It uses those boundary files to create the.
Yeah. It doesn't matter what it is as long as you have an underlying digital boundary file. So in other words, for each spatial unit, you have a series of linear line segments with coordinates for the origin and the endpoint. And so these line segments define the boundary. So how can we get around this? By using a project file. I'll show you in a second. But first, let me show you what this weights file looks like. So this GAL format is something that was developed a long time ago, and so this is the structure of your spatial weights file. It's a text file, which means you can edit it, which I don't recommend, but if you really know what you're doing, you can edit it, right? Top line is the header line. It gives you how many observations that there are. This is used later on to check and make sure that you're not mismatching the weights with a different size data set. It gives you the name of the original shapefile from which it was constructed and the key, the ID variable, right? And then after that, there's just numbers. And the numbers are the ID for each location, followed by how many neighbors there are. So for the first one, there would be 3 neighbors, and then the IDs for those neighbors. So this file is what we call a sparse representation of the weight structure. Sparse because it only contains the non-zero points. As I mentioned the other day, most of these spatial weights are mostly zeros, more than 99%, right? So we don't want to deal with the zeros, we only want to deal with the non-zero elements. So that's a GAL file. Okay, so let me go to the project so I can show you that. Yeah.
So you can set order of continuity and get neighbors, right? Or 2 neighbors or something. But is there a way to set like distance? So
Yes.
say 2 miles out or something? Or
Yeah, that comes next. So just if you look at this, you see there's 2 parts to this. The top is contiguity weights, and then the bottom is distance weights. And we'll get to that in a second. So what I wanted to show you was the project file. So if we do, well, you can check project information, and it gives you, but not very much. It's just kind of a summary of the stuff that's in there. Where is this data come from? So what kind of a source is it? It's an Esri shapefile. So it's kind of summary information. But once you save the project, so we're going to save project, and it's going to ask us, yes, it's going to ask us for a name, so I'm going to call it Nat Regimes, GDA, okay, and it's saved successfully. So now if we go here and look at this, well, this is an XML file. If you look carefully, you see all the different variables are here. And then here is the queen weights. It knows that it's a queen weights. And it knows that it's symmetric. And here's the rook weights. But for the rook weights, since we loaded that, it doesn't know anything, right? So again, if you know what you're doing, you can go in there. It's a text file, XML. You can edit it. And you can put in rook. And then the next time it will know that it's a Rookwe. So I'm going to live dangerously here. So I think I can do this. We'll and call it Rook. Let's see if this works. So now I'm going to exit everything. I don't want to save my data. And I will, instead of loading a shapefile, I will load the project file. And now we go to the weights manager, and the weights are there. And I did it wrong, yeah. Whatever I did, I didn't do it right, so. Oh yeah, I put it in the wrong one, but, okay. So, but you see the idea, right? So let's get rid of this one. So I don't have to do anything. The weights are already in there, and we have the metadata on the weights. So if you're going to do a lot of manipulation, a lot of different weights matrices or weights files, also if you do space-time analysis or you do a lot of these grouping things, the project file remembers that. So then you don't have to redo them, basically. And we're working in GeoDa to get more and more of that to be recorded so that you have more of a history, so to speak, so that, you know, when you pick up the analysis where you were before, you don't have to redo everything. And in part, that's also where you see recently analyzed files. You just click on them and they load up. So anyway, this is now the first part. Let's look at the, so the first part meaning the contiguity weights. Now let's look at distance weights, and let me load a different data set, which is a point data set, which is a little more appropriate. I will get back to this in a minute. So this is a point data set of, it just happens to be kind of pretty random, not random, but house sales in central Cleveland in 2014. And to show you, it's hard to see, you know, our point cartography is not the greatest, but one thing you can do is put in a base map. So if you click on this icon, you can pick, as long as you have a projected data set, so it knows the projection, you can pull in a background map, which is then makes it almost impossible to see the points, but I don't know what happened to the points. Oh, I have to change the transparency. There they are. So now you see the points, and you can more or less situate them in space. So for the points, so for area units, the natural definition of a spatial weight is based on contiguity, on common boundaries. For points, a natural definition is based on the distance between the points. So in GeoDa, we again need an ID variable, and that is unique ID. So now we're going down here, and we click on the threshold distance, and you'll see a distance measure pop up. Okay. The coordinates of these points are actually projected, and they're in feet. So the distance that pops up as the critical distance, as the threshold distance, is the largest nearest neighbor distance. So the nearest neighbor distance is the distance between a point and its closest neighbor, right? And we take the largest one of these. That ensures that every point has at least one neighbor. But it also means that the number of neighbors for all the points is determined by this largest nearest neighbor distance, which can be very large. It all depends on the distribution of the points. If they're kind of evenly distributed, that's not a problem. But typically what we have, like in Cleveland, is that a bunch of points are fairly close together, and then some are really far apart. So the ones that are the furthest apart will determine this critical threshold distance. And as a result, the number of neighbors will vary a lot. So let's create this weights matrix first, and then we'll look at things. So I'm going to call this D1. And again, we see in the weights manager, we see the characteristics. We see even the distance that we used as the critical thresholds. Right? So again, it's a good idea to save the project file so that we have this information for later use. Okay, let me go back, pull in the net regimes. So the weights manager not only lets you create and load and remove weights files, it also lets you look at the characteristics of the weights files. And there's two important characteristics that we are concerned with. First one is the distribution of what is called the neighbor cardinality. So that is the distribution of the number of neighbors. So how many observations have one neighbor? How many observations have two neighbors? And so on. So what you want to see here is a distribution more or less like this. Nice and symmetric, not too great a range, so that the number of neighbors is basically very even throughout the data set. Why is that important? We'll see that next week when we talk about the concept of a spatial lag, or a spatially lagged variable, which is how we will pull the spatial dependence into the specification of our regression model. And this spatially lagged variable uses the weights to compute an average of the neighboring values. So because it is an average of the neighbors, we want the number of neighbors on which this average is computed to be more or less stable. And this is a very nice typical situation where not too many crazy things happening. And we can quantify this by right-clicking on here, and any, let's see. Why doesn't it show the statistics? The what? I right-click? Oh, view, yeah. So then you can quantify this, and you can actually see what is the mean, the median of the number of neighbors, and in fact, each category on there as well, right? So every graph has this view display statistics thing, and I should know this, but you know. Yeah. The statistics, I don't believe so. You can't export them, right? No. Only the graph. Yeah. In the parallelogram, then the statistic is exported, but the graph can be exported.
Can you export which counties are the neighbors?
Yes. Not which, how many?
Just how many?
Yeah, because which are the neighbors, you have that in the GAL file. So your weights file has that information.
Right. So I'm thinking, like, if you want to export it and do something with it in a statistical package just with the neighbors or something.
Well, I guess I don't fully understand your question. If you want to know how many neighbors each observation has, that you can save connectivity to table. So that will create a new data column in your table that has the number of neighbors in it. See the number of neighbors. If you want to do something with the neighbors, then it depends what it is you want to do. So if you want to compute, say, an average value for the neighbors of a specific attribute, specific variable, that is called spatial lag. And you can actually do this in the variable calculation. Here's the spatial lag. So then, you know, if you want to do it explicitly, you would have to take the text file, that is the GAL spatial weights file, and somehow parse that, and then pull the IDs out of that, you know. Okay, so the connectivity histogram is one way to get a sense for the distribution of the neighbors. The other characteristic, illustration of that is the connectivity map. And the connectivity map basically lets you move through the data set and show which are the neighbors. And the neighbors are highlighted. It's a little hard to see on the screen, I think. But you could see it, you know, you can adjust in the options, you can adjust the setting for the contrast between highlighted and regular observations. In the old style, you use cross-hatching. So if you want to go back to the old style, you have preferences in GeoDa. And so use classic cross-hatching, and I'm not sure if this works here. It should, but I've never tested it. So then if you, see, this is the way it looks in the handout. So in the handout, you have the old style cross-hatching, and it gives you, for any county that you point at, it highlights the neighbors, and then on the bottom, on the status bar, it gives you what are the neighbors. So this is something that you can use as a quick check to make sure that the structure that's embedded in the spatial weights file is in fact matches your expectations. And this is where you pick up issues like where you need the fuzzy boundary comparison, because you would look at the map and you would say, these look like they're neighbors, but they're not highlighted as neighbors because this information doesn't come from the map, it comes from the weights file. So if you encounter situations like that, that is where you will need the fuzzy boundary criterion. Okay, so then let me switch back to the other data set. I don't want to save my data. So I go back to the Cleveland data set, and I will pull in the data set, or what I could have done is just click on this. But as far as I know, this will not pull in my project file. So if I do this, I get the points, but I don't have the weights, right? And so if I wipe this out and I open this in and I pull in the project file and I do the weights, I have my weights in there, right? That's the advantage of the project file. What I wanted to show you is the connectivity histogram for a distance bandwidth. So you see right away, this is a mess, right? You know, the average number of neighbors is basically 13 as compared to roughly 5, so it's more than double. And the distribution has an incredible range, right? So some of these points have many, many neighbors and others do not. And now, how can we see this? There's this concept of linking and brushing, which underlies everything in GeoDa. So if you select anything in any graph, and this is the new selection, it highlights, it makes it dark, then all these points are selected in here. And you see the dark ones are all the ones that are really close together. And they have a lot of neighbors. because the critical distance is based on these, which are really far apart. You know, so you see these little red, it's kind of hard to see. If you do it live, you see it, these red points are far away from each other. So that drives the critical distance. So the critical distance, you have to remember, is a max-min criterion. So it's the largest of the nearest neighbors. So that will be driven by the points that are the furthest apart, right? And this also can be used for polygons. I'll talk about that in a second. So right now, I've made this, so far, I've made the distinction between aerial units, polygons, and connectivity, contiguity, points, and distance, right? But it doesn't have to be that way, as we'll see in a few minutes. But before I go there, I wanted to show the other type of distance weights, and these are k-nearest neighbor weights. So you have to set the ID variable, and then this all becomes available. So k-nearest neighbors ignores the actual distance, but takes as neighbors whoever is closest. So if you say 4 nearest neighbors, it's whatever distance they are, as long as you're up to 4. As I mentioned in class the other day, we have a problem when we have ties, because there isn't really any straightforward way to deal with ties. So either you include all of them, but then the k is no longer strict, right? If you say k is 4, and 3, 4, and 5 all are the same distance away, which of these 3 are you going to pick, right? And so one way to deal with this is include them all. The other way, which is what GeoDa does, is to randomly pick the ones so that we have exactly k equal for all of them. So then, yeah.
Is it ever possible to pick neighbors in a particular direction? Like, for instance, I'm looking for my neighbors that are closer to the city center than I am.
As it is now, I don't think so, but there might be a way to trick it into doing that. Yeah. So you would basically take neighbors and then subset those neighbors using a second criterion, right? You can do that in PyCell. So in PyCell, which is a Python library that includes a lot of the weights manipulations, you can do set operations on weights. So you could create your weights in one criterion and then have like a mask, right? You say you only want the ones that are closer to the city, and then you would apply that and create a new set of weights. GeoDa doesn't have that functionality. I'm sure you could do it in R2, but I just don't know off the top of my head how you would do it. Okay, so when we create these k-nearest neighbor weights, just think for a second, what is that going to do to your connectivity histogram? Yeah. So it's like this, because they're all exactly 4, right? So this isn't that useful, but the map is useful because sometimes the map will show you really how counterintuitive this may be. This is kind of hard to see, but I don't know if you, can you even see it? Yeah, they become black, right? So you see the neighbors for any given point. And so when you move over here, you see how far these are? The 4 I mean, there's no islands. Everybody has exactly 4 nearest neighbors, but the distance distribution is very different. You know, here these are all very close. The other ones are very far. In other words, you have to make an assumption that the effective distance to k is kind of warped. You know, it's not a linear effect. In that, in other words, what you're saying is that if you go to a grocery store in Wyoming, you don't care that you have to drive an hour. If you go to a grocery store in downtown Chicago, you care if you have to walk more than 10 minutes. Okay, that's the closest grocery store. It's the same as the closest grocery store, but the distance that it takes you to get there can be vastly different. And so that is potentially, depending on the application, potentially an issue with k-nearest neighbor weights. What they give you is that you have complete control over the number of neighbors. And as we'll see later, that has implications for certain things, estimators and tests. So it's always constant, it's always the same. But unless these distances are fairly uniform, you're making some fairly strong assumptions about the spatial interaction and the effect of distance on the spatial interaction. Right? It becomes more of what in geography is called intervening opportunities. So it's whatever is the first thing. And if it takes you an hour to get there, it is still the closest grocery store, and that's all you care about. You know. So this is something I wanted to show you. Another kind of gotcha I wanted to show you is if you are stubborn and violate this threshold. So say, you know, for theoretical reasons, you would, I mean, this 3,800, where does that come from, right? That's purely driven by the data. But you say, okay, it should be 1,500 feet. So I'm going to set my distance band at 1,500 feet. And there's absolutely nothing wrong with that, except that you will create isolates or islands, and there's this long warning to tell you that. And what I have to say yes. I'm going to do it anyway, just because I want to show you. So we have, yeah. So now we have this weights matrix, and we're looking at the histogram, and here you see 24 observations don't have a neighbor. Right. And if you click on this, then you see which ones they are, if you can see it. They're these red ones. So these are all points that are fairly far away from the other points, and more than 1,500 feet, so they don't have any neighbors. And that is a problem. We talked a little bit about that last time. We'll talk about it again when we get to the regression analysis. Basically, for all practical purposes, that means that these observations are not included in the spatial interaction part of your analysis, because they are, in fact, not playing. They are not interacting. They are too far apart. Okay? So then let me show you one more thing for the points, is that we can do contiguity for points. You might say, well, how does that make sense? And we, as I mentioned, we can represent the points by polygons. And these are the Thiessen polygons that I mentioned earlier. So now it's all still the same geography, but it's a different representation. Rather than taking the points, we represent these observations as the polygons. And so now we can do contiguity for these polygons. In GeoDa, that's all done under the hood. You don't have to worry about it. So if you have points and you pick clean contiguity, you will have a contiguity file, you know. And I had it already. So you have your contiguity file, and then in the list, if we look at the histogram, this is a nice and balanced histogram again. So this is an alternative to the k nearest neighbor. So the distance bands for highly irregularly distributed points is a mess. You know, you have a whole range of different distances. Some have 30 neighbors, some have 2 neighbors, so that's really unbalanced. So you can go to k nearest neighbors, where every unit has the same number of neighbors, or you can change the representation and go from points to polygons and then do contiguity on those polygons. And that very often gives you a much more balanced neighbor structure. So it's close to nearest neighbor, but it's in multiple directions, so it's a little more balanced. And similarly, the parallel to this is if we go to our counties, we can do distance-based weights. So we have the Phipps number here, and then if we want to create a threshold distance, we can pick it. Now, here we have a problem because, and I hate to bring this up because I know you guys are allergic to this, the notion of a projection. You know, the Earth is not flat. Some people think it is, but it isn't. So then our representation of the Earth is in a flat map. So we have to do a mathematical conversion to get from basically degrees, longitude, latitude, to x and y coordinates on a flat map. And there are many different ways of doing this. The main thing you have to remember is whether or not your data set is projected. If it's projected, the x and y coordinates will be in something like meters or feet. If it's not projected, they will be in decimal degrees. Latitude, longitude in degrees, you know. If it's not projected, you cannot compute a Euclidean distance between degrees. I mean, you can, but it doesn't make a lot of sense. So if your data is not projected, then you have to compute something which is called great circle distance or arc distance. And so in this particular example, for the counties, the data is not projected. So then we take the arc distance, and you see immediately the critical distance switches from this crazy, you know, meaningless units computed from the decimal degrees to 90 miles, which is basically the distance between two of the largest counties in the US, in the west, San Bernardino County and its neighbor. San Bernardino County is a little bit east of Los Angeles, and it's the largest county in the country. So again, you know, just as we had with the points, that the points that were the furthest apart from their nearest neighbor drive this critical distance, the same thing will happen here for the polygons. The largest polygons will drive this critical distance. This is often a problem in practice when you deal with census tracts for metropolitan areas. So the census tracts in the center of the city, you know, they're about 3,800 people. They're all very similarly sized. As you move outward into the suburbs and the sprawl, these tracts get larger and larger. So if you do a critical distance criterion, it will be determined by these huge census tracts on the outlying areas of the city. In some work I did a long time ago, we worked on Miami, and Miami is surrounded by the Everglades, and some of the census tracts in outlying Miami are in the Everglades, and they're absolutely humongous. So if you don't pay attention and just do this mechanically, the distance between the centroids of those Everglade tracts will drive your critical distance, and then every census tract in downtown Miami will be a neighbor to every other census tract in downtown Miami. And we said last week, you cannot have that everything is correlated with everything else. So these are the kind of traps that you might fall into if you do this mechanically. Never do this mechanically. Always look at the connectedness structure, not only to pick up problems with islands or isolates, but to pick up problems, the multimodality that I mentioned the other day for, say, counties in Virginia and other weird things. Now, what do you do with these weird things? There's no theory there, right? There's nothing you can do about it. You have to make ad hoc decisions. And for example, you have to decide whether an island is truly an island or should be connected to something on the mainland, right? You have to decide what to do when your distribution of neighbors has too large a range. Do you go to a Thiessen polygon situation, or do you go to k nearest neighbors, or something like that? Each of these decisions has implications because these weights determine the smoothing that goes on when you compute your spatial lag. And smoothing is not a good thing. You know, statistics is about variability and variance. Smoothing is about reducing the variance. So if you reduce the variance too much, everything is a constant, and you don't have anything left. So this is something to keep in mind when you do these operations. And let me, in the time that's left, do two things. So this is GeoDa. You have a handout. It's on Canvas. It goes blow by blow on, if I forgot something, it's in there. So you can look at that. What I did want to show you, because it is reported in the book, in the Modern Spatial Econometrics book, but I just want to show you real quickly the interface for GeoDa space. And so this is the GeoDa space interface. It's a little bit different because it's focused specifically on regression, and we'll talk about this in more detail next week. But the weights are there. You have two kinds of weights. You have the model weights, which we can create. Let me pull in a data set first. So let me put in the database for NAT regimes. So you see this little interface. We'll pull the variables in different boxes depending on the model specification. I'll talk about that next week. But I wanted to show you the weights. So we can create weights here too, or you can just load them. So if you load the weights, for example, we go to the NAT regime weights, and we have our queen weights again. There they are. And then we can check the properties of the weights. And it's a little, less visual, but it's basically the same thing. For every observation, it tells you what are the neighbors. So you can scroll through here and pick a different neighbor, and it will give you the weights. And the cardinalities are here. This is the information for the histogram. And you can do a little viewer just like we have in GeoDa. You can take the shapefile, and then you can find the neighbor structures, just like in GeoDa. Right? So just what I wanted you to know is that the formats that are supported by GeoDa space are exactly the same as the ones that, in fact, there are fewer in GeoDa space than in GeoDa. GeoDa, let me rephrase that. GeoDa space only works with D-based files and shapefiles. But GeoDa space can read multiple format weights files. GeoDa only reads its own weights files. So GeoDa space can read weights files in the formats created by ArcGIS or the MATLAB Spatial Econometrics Toolbox, or GeoBugs, which is an old version of bugs that did geographical analysis. So GeoDa space can read all those kinds of files. Then you can read them in GeoDa space, you can save them as a GAL file, and then you can pull them into GeoDa. So then, finally, I want to spend about 15 minutes on R. So we'll revisit GeoDa space many times as we get into the different types of regression models that you see down here. All the different specifications that we'll talk about are covered in GeoDa space. And always have a hard time. So R has this fairly new thing. It didn't have it yet in the fall, so in my fall class I didn't use it, but so I'm a big fan of notebooks, and those of you who do data science type things are probably familiar with Jupyter notebooks. And Jupyter notebooks were originally developed for Python, but now support many other things, including R. Installing R in a Jupyter notebook is not that hard, but it's not straightforward either, right? And it's a particular style of working, and I like it a lot. But then RStudio, which is a graphical user interface that you can use with R, has introduced its own set of notebooks. So it's kind of obscure the way it works, but RStudio has these notebook files which are a particular kind of HTML file. So you have the handout on how to do spatial weights in SPDEP on Canvas, and there's also this file here. And so when you go down here, you can do show the code or hide the code. Basically, that pertains to this HTML file, which looks just like your Jupyter notebook. It's text and then code and output. But you can also save this as a R Markdown file. And as I discovered this morning, this doesn't work in Safari, but it does work in Chrome. It used to work, because that's how I got them to begin with, but when I tried it, see, it does this kind of thing. And so then you need to save that. But in Chrome, it does it the way it's supposed to. It creates this RMD file, which is this file right here. And so if you go to RStudio, we go make sure you set, I should turn this off. So you go to the directory that has it, and you set it as the working directory. And then in RStudio, actually, you could just double click on this, and it will launch it in RStudio. So this is a, let me see. This is an R Markdown file. It doesn't look as nice as, say, a Jupyter rendered notebook, but you have the rendered HTML. And the one thing that it does do, which is new, I mean new since the fall, is that you can run through the code by just clicking on this little arrow button. And that will, just like in a Jupyter notebook, Shift Enter, which executes the code, this will execute the code in the notebook. Now, the way R works, or RStudio works, if you have code in the script window and you highlight it and you execute it, it gets executed on the command line in the window below. This also happens, but you don't have to look at it because it shows up right in the notebook. So in the few minutes that I have, let me just, I have 10 minutes, right? I'm still confused about this. But so I'm not going to race through this, okay? You have this. You can do this at your own pace. I'm going to highlight some things and talk about some features to keep in mind, right? First, I'll show you the mechanics so you see how it works. So this is gobbledygook. You know, this is R-specific. This is to make sure that when I run the code that you actually see the results and you see all the errors and all the warnings. You know, R Markdown is really designed to produce reports so that you can have dynamic reports. So if you're, say, you're doing a regression analysis, you know, every month you regress the same variables on the same other variables, but every month your data set gets updated. So rather than doing this whole thing over and over again, you have it in an R Markdown document where you just run through the code again, and all the results and all the tables and all the graphs are updated, and you're good to go. That's really why it was designed. But it has a lot of other uses. For example, I find it very useful for teaching because I can never remember these commands, and I make just one typo after another, so nothing works, so I end up spending most of the time fixing my typos, right? Here, it's all done, right? I did it once, it works. All I have to do is click the little button with the arrow, and it runs the code. It's always the same thing. And I can fine-tune it, and if I look at it again 2 months later and I think of something, all I have to change is a couple of lines rather than doing the whole thing all over again. So if you, I mean, it's definitely worth investing in. Either one, the Jupyter notebooks or these notebooks. The nice thing about the R Markdown notebooks is that they are kind of integrated with the whole publishing, you know, ecosystem. So you can turn these into papers, very nicely formatted papers, into PDF, even into Word documents, you know, just one click, you know, and that's, here you have this knit thing. I really recommend this if you're going to write papers or theses or reports. Invest a little bit and figure out how this works, because it's incredibly simple, but also incredibly powerful. So you can make your whole analysis, you know, I wouldn't say automatic, but near automatic. When your data update, everything updates, you know. So you can write a book a week, right, with a new data set. People who work in financial institutions, this is their bread and butter, because the data just constantly change and they have to update the analysis, and it's just one line and you get a new report. Okay, so as I said, this is a little gobbledygook that I have to run just to make sure. You'll see the little green bar next to the code. If it works, it's green. If it doesn't work, it's not green. So what we are doing here is first we load the SPDEP package. So the weights functionality in R is contained in the SPDEP package. There's a lot of weights functionality in R. I don't cover most of it. I just, because this is my own bias, my own preferred way, I always make my weights in GeoDa. GeoDa is the fastest and most robust way to create weights. They're all text files anyway. R can read the text files, and then you can do other things with it, as is illustrated in this notebook, like creating inverse distance weights files, which are not supported yet by GeoDa, but will be soon. So these kinds of things give you additional flexibility. You can create weights in R from shapefiles and from point data sets. It requires a little bit more learning than I have time to do. You have to be familiar with the different ways in which R stores geographical data, and then depending on how it's stored, different functions apply. But that's easy to learn if you care to do it. So I'm loading the library, and you see in the red underneath it says I loaded the dependencies. This is the kind of thing you would see on the command line as well. So we go down, and here the main command is read.gal. So I purposely did this wrong so that you would have an error message. And this is again to drive down the message of the importance of the ID variable. By default, when R reads a GAL file, it takes the observations as being consecutive. So it just numbers them 1 through 3085 in this case, and works with that. But as you have seen, we put in FIPS codes. So we keep track of these things with FIPS codes. So in order for R to actually read those codes from the GAL file, you have to do an additional command. You have to specify override ID equal true. Don't ask me where that comes from. Somebody thought it was a good idea at some point, but this is what it is, right? And so then now everything works fine. We can list the object. It gives you a very quick summary of what's in there, or we can run a summary and it gives you the cardinality of the observations. The way you know that this is right is because you see the FIPS codes in there. If you did it the other way, then you would see 1, 2, 3, 4, you know, very small numbers, and then you would know that you haven't done this right. So this is all pretty straightforward. Since I don't have a lot of time, let me move to the GWT file, and you can run this on your own. Just in a nutshell, what the problem is. There is no command read.gwt. Okay? It is for whatever reason, read.gwt2nb. Okay. And write this down, because I had so many people come to me in the fall class say this doesn't work. And I looked at their code, and sure enough, it said read.gwt. That command does not exist. Okay, so you have to use this one. Of course, you could put in an alias. You know, if you were clever, you put in an alias so you don't get trapped. But so the other difference is that instead of reading the ID from the file itself, read GWT needs to have that variable already specified. So it's a two-step process. Read GAL is a one-step process. Everything is there. Read to get the GWT file in, first you have to read the data set, specify the ID variable, and then you can create the file. These are neighbor lists. They're not weights. To create the weights from the neighbor lists, you have to convert them. And that is another command. So you have to actually go to this command here, nb2listw. So very important in R, in SPDEP, there is a difference between the contiguity structure, which is contained in a neighbor list, and the actual weights, which are called list weight objects. And so the weights actually have the values of the weights. The neighbor lists do not. Right? So you always have a two-step process. You know, you have the GAL file, you read the GAL file, then you convert the neighbor list to an actual list W object. And then you can compute spatial autocorrelation coefficients and the whole deal, and use them in spatial regression analysis in R. You will need a list W object, so a list weight object. So that's very important to know. If you look at the document, I'm out of time, you will see that there's some trickery in there that I show you how you can pull actual distance measures out of one of these GWT files and then create an inverse distance weights matrix. And you also see some fancy graphs that show you the neighbor structure as a network. Let me see. I have NB1. Okay, let's see if this works. I have to load the data set. There you go. So that's the network representation of the neighbor structure for the points in Cleveland. And as you see, it is very weird, right? This is because of this distance band. You basically have a couple of disconnected subnetworks. And you know, if you do this, if you go through the notebook, you will see that it's very much cleaner when you use the Thiessen polygon approach. So all that stuff is in the notebook. You can walk through it. So now you have, or you should have, the means to create, manipulate, and analyze spatial weights in GeoDa space, and to some extent also in SPDEP if you're going to work in R. Okay? And so this is it for today. And then on Wednesday, again, I apologize, but I want to make sure everybody's on the same page. We're going through very quickly everything you ever wanted to know about ordinary least squares and two-stage least squares. So very quick revision.